Have you ever looked up at a looming thundercloud and wondered what incredible forces are at play to create such a spectacular light show? Charge separation in thunderclouds primarily happens due to collisions between ice crystals, graupel, and supercooled water droplets within the cloud. These frequent interactions cause a transfer of electrical charges, with heavier particles typically taking on negative charges and lighter particles becoming positively charged. The core mechanism behind this electrical buildup is the constant movement and friction within the cloud. Strong updrafts carry warmer, moist air and lighter ice crystals upward, while graupel, which are soft ice pellets and larger ice particles, tend to fall downward due to gravity. As these particles move past each other, they collide, and electrons are stripped from one particle and transferred to another. The specific charge transferred depends on factors like temperature, ice crystal size, and collision speed. This means that in many thunderclouds, lighter, positively charged ice crystals accumulate in the upper regions, while heavier, negatively charged graupel collects in the lower parts of the cloud. This distinct separation of positive and negative charges creates a massive electrical potential, much like a giant battery, ready to discharge. An interesting detail is the role of supercooled water, which remains liquid below freezing temperatures. When supercooled water droplets collide with ice crystals or graupel, they freeze on impact and can influence the charge transfer. For example, during a collision, supercooled water might freeze onto a graupel particle and capture positive ions, leaving the rebounding ice crystal negatively charged. Understanding this process helps scientists predict lightning behavior and even study the conditions within severe storms. So, the next time you see a powerful storm, remember that it is the continuous ballet of ice particles and water, driven by strong winds, that orchestrates the dramatic electrical display, highlighting the invisible forces at work in our atmosphere.